Okay, so yeah, we're going to go over the second half of the homework, and these two chapters, chapter 15, chapter 16, are related just a little bit in the mathematics. So I will be drawing a few details from chapter 15 into chapter 16. It'll just make chapter 16 a little bit easier. However, this is a distinct chapter as far as the type of motion that we are talking about. So chapter 15 was simple harmonic motion. Just to give you just sort of a real quick 30-second review of what happened with simple harmonic motion is that we defined a position function x of t to be equal to an amplitude times a cosine of omega t. This is a function of time now for the position, and this just describes a cosine wave with some oscillations between a positive amplitude and a negative amplitude. And the types of objects that undergo this type of motion, this one right here, an x position, is for your block on a spring. And this block is vibrating back and forth along the spring between your positive A and negative A, your positive amplitude and your negative amplitude. And from this position function, we then take two derivatives and we get some equations for the amplitude of the velocity and the amplitude of the acceleration. And those will still be in play in chapter 16 as well. However, unlike in chapter 15, where we were using a wave to describe a type of motion that is cyclical, in chapter 16, we are actually describing physical waves. So what we mean there is if you have, for instance, a rope that is attached to a post, and maybe there's a little ring down here, you can stand at one end of the rope and you can shake the rope. And when you shake the rope, you'll send a wave pulse along the string as long as it's sufficiently tight. And it'll usually just look like a disturbance like this. And that wave pulse is going to travel down the rope. It'll hit the ring post system kind of thing at the end. And then if that ring is allowed to move up and down, then your waveform will actually come back on top. And if that end happens to be fixed, the waveform will come back along the bottom. You don't need to know that necessarily. That's usually something that's just like covered when they're introducing the idea of a traveling wave. But the point here is that we want to describe this actual disturbance with an equation. And so we have this pretty long, complicated looking equation. Whoops. And I'll go ahead and write it here and talk about it just a little bit. So the equation is this whole long mess, y of x comma t. This is a function for the y displacement of, for instance, your rope. So if you were to draw like an xy axis, you'd have the x-axis here and the y-axis here. So this is going to be an equation which will tell us for some point on the rope located at some x position, what is the y displacement? Well, it's not enough just to know where in the x it is because this wave is traveling. So you also need to include some consideration of time so that you can figure out where along the rope your wave disturbance is. So you need a function. If you want to find a y displacement for a point along this rope, you need a function which considers both your x and then also t so that you can see how the wave is moving. So that's why we have a function for both in terms of both x and t. Okay, so let's look at the rest of this mess. So this is going to be equal to y sub m. This is y max, and this is just your amplitude. This is big A, in other words. This is how far that wave could possibly be disturbed. And then this is also going to vary with a sine or cosine. In this case, we choose sine, and we, without really getting into why we use sine instead of cosine, just know that when we're doing traveling waves, it's going to be a sine. And okay, and then in the inside, we're going to have one sort of old familiar, which is omega t. And just to sort of refresh why we had omega t in the first place in simple harmonic motion, we knew we wanted a function in terms of time, but we know that sine or cosine can only be evaluated on radians. So we needed to turn our seconds into radians. So we multiplied our seconds by radians per second. Okay, so cool. So we just sort of carry that over. We have the omega t term inside the parentheses. That sounds good. Additionally, though, we now want to include a term which uh, enables us to input information about the x position along the string. And so we know we're going to want a variable of x. And just as we had to adjust our time to be in units of radians, we also need to adjust our x, which is a meter. We need to adjust that meter. So we need something that has units of radians per meter. Now, we haven't actually defined anything that is radians per meter yet in this class. So this is a new quantity. And I also need to mention that this quantity is going to repeat a letter that we used just in chapter 15. So we want to kind of put that away. The letter that we use is K. And I'm actually going to use a different color here to highlight that this is kind of a new consideration in this equation. And this K is called the wave number. And we're going to have some equations that have to do with the wave number. The one that I'll go ahead and give you is that this K is going to relate to the wavelength with K is equal to 2 pi over lambda. Most of you have probably encountered a wavelength at some point in your life, but just as a reminder, if I wanted to find the wavelength of a sine wave, and I know the sine wave does this, that's one complete cycle of the sine wave. The wavelength is just how long a single cycle is. That's something that you do need to be able to do. You need to be able to read a sine or cosine graph and find the wavelength. You notice that you can only take the wavelength so long as you have an x position. So that's why your wave number is related to the x variable and not the time variable. So you need an equation, rather a graph that has x as the independent variable. Okay, so that's one new thing, is that we include a uh, a, a distance variable, within the sine function. The other thing is we need to somehow combine these two together inside of the sine function. And we don't want to multiply them together, obviously, because then you'd have radians squared. That's not helpful. So instead, what we actually do is we want to add these together. The way that we add them together is a little complicated. So I'm going to use a symbol here that I always just use so that I can keep straight how I'm going to add them together. It's the minus or plus symbol. I think in your homework and probably in the lectures as well, they use plus or minus. Here's why I use minus over plus. We need to choose a minus or a plus based on the direction that the wave is traveling. So if you see a minus sign, that means that we're moving in the positive x direction. And if you see a plus sign in there, the plus sign actually corresponds to a negative x direction. So notice that these are kind of flipped from what you'd assume. You'd assume that the plus corresponds to the positive direction, the minus corresponds to the negative direction. It's actually the opposite. So just make sure that you know this and that you sort of memorize that rule and that you internalize that. There is always sort of implicit inside these parentheses, there's always one other little term that I haven't put here, and that is the phase shift. So if I were to write this as a general equation, I would also have inside of here plus phi for the phase shift. This is for a wave which doesn't happen to start at 0, 0. So you don't necessarily want to sign, or 0, 0, 0, I suppose, because it's three-dimensional. And maybe you don't want, so you don't want a sine wave. You want to be able to shift that sine wave to the left or the right. And that's why there's usually a phase shift in there. However, 9 times out of 10, you're not going to need it. We'll have one homework problem where we are going to need it. But for the most part, this is going to be the equation that we need to be responsible for creating and also for reading. One other note that I'll make, because this has been an old exam question, is on the direction notes. So we have a negative corresponds to positive x direction and a plus corresponds to negative x direction. That's fine. There have been homework, or rather exam problems that have done something like this. Y of xt is equal to y max sine of kz minus omega t. And then I think they did have a plus phi, if I'm remembering this exam question correctly. So they just give you this function, and then they just ask you, what's the direction that this wave is moving? And a lot of people got this problem wrong because they did the one part one, which is to say, okay, I have a negative sign there, so I know that I'm moving in the positive direction, right? But the answer choices for this give you something like, answer A is the positive x, answer B is the negative x, answer C is the positive y, answer D is the negative z, and answer E is the positive z, something like this. And so you'll notice that we have other directions other than x indicated. And the only way that we can tell which direction x, y, or z that this thing is moving is by looking at this variable right here. So I know that it's positive, which means that I can rule out my negative answer choices. But then since my kx is now a kz, that tells me that I'm actually moving in the z direction. So that's just one note that I want to make as far as dealing with the directions. I think there's the homework problems that you have assigned in this chapter are very, very long, a lot of different parts. And they I had a point that I was going to make. Oh, that I do think that they ask about direction at some point. Yeah, I'm looking at problem number 7, and it does. Okay, so I think there are going to be a number of equations that are associated with this general function here. We have one for the wave number. We know k is equal to 2 pi over lambda. Let me go ahead and start kind of a list of what we have. Our wave number is equal to 2 pi over lambda. Our omega is still 2 pi times the frequency, f. Omega is angular frequency, f is the frequency in hertz, if you ever see hertz. We also, now that we have a wave that is actually traveling along a wave, along some object that is disturbing, and it's actually moving with some speed, we can also describe the speed. So we're going to have two different definitions. The first one is v equals lambda f. This is a very important equation because it allows you to find the speed of a wave so long as you know its wavelength and its frequency. So wavelength is how long the wave is. Frequency is the number of waves per second. So that's what a hertz is, 1 wave per second, 1 hertz. Okay, and in light of our definitions for the wave number and for omega, we can also generate an equation that will give us a speed in terms of those two. It would be, let's see, we want omega over k. Omega over k, and then your 2 pi will cancel, and you'll recover lambda f. Cool. So if you're asked to find a speed, it'll generally be one of these two. And beyond that, I guess we could sort of start talking about the actual problem-solving technique. So I've thought quite a bit about this, the way that you should tackle these problems. And I think that the best way to approach this is assuming, as we will when we're doing the actual math problems, we're going to have waves that are moving in the x direction and disturbing in the y direction. It'll be a y of xt function, and there will be a kx inside. So assuming that, what you want to do when you're actually attacking these problems is split up into the x and the y. Let's go back to this old tried and true method of attacking these types of problems. This goes all the way back to the beginning of the semester. Let's split up what's going on in the x and the y. In the x direction, you have your wave movement. Your wave is actually moving to the right. It's moving in the x direction. So in the x direction, you have things like your v equals lambda f, or v equals omega over k. And yeah, so, and then you also have your definitions for lambda, your definitions for f. So if you'd like to copy those down, you can. But those are generally the things that we're going to be doing with the x direction. It's actually similar to just like 1D motion, where you just have a speed. It'll be a constant speed, and you're moving in the x direction. In the y direction, the tools that we have at our disposal are essentially the ones from simple harmonic motion. So that means that we have things that we can do, like your y max is equal to the amplitude, which we are calling y sub m here. And then remember the maximum velocity from simple harmonic motion was a times omega, where a was the amplitude. So now our amplitude is y max times omega. And your maximum acceleration in the y direction will be y max times omega squared. Those are just kind of the simple harmonic motion maximum functions. Yeah, and then the associated frequency will be still that 2 pi f, or 2 pi over the period. And any considerations of energy or anything like that will typically come from sort of, your y side. So let's go ahead and tackle a problem. It's kind of a long intro, but it's because I think that this equation is kind of complicated, but once you get used to working your way around the equation, the actual problems that you need to do to solve it are usually like one-step problems with little short calculations. Okay, so problem number 7, we have a sinusoidal wave moving in the positive x direction. They give us a speed, so we're fine with that. We note that speed is going to be a v, so maybe we'll go ahead and write that down. My speed happens to be 85 meters per second. And this is your v that is equal to lambda f, or equal to omega over k. At a certain time and position, so t equals 0, x equals 0, the initial condition has a transverse displacement of 4.3. Yeah, Nina, so I have a recording from, we went over those in discussion, and I have a recording that that I'll be posting. It's on a different chapter, so it makes the most sense to kind of split it up anyway. So I will post that once I finish up in here. Cool. All right. Okay, yeah, so they give us this like initial condition. At t equals 0, x equals 0, you have some transverse displacement. So that would be a y of 0, 0, x is 0, t is 0, and it's 4.3 centimeters. That's what that means mathematically. We'll see how we actually use it in just a second. And oh, they also tell us that it's not moving. So that's tight. That means that our v, I should call this v sub y, 0, 0, is equal to 0, because it's not moving, 0 meters per second. Now, here's a point that I want to make real quick, is that this is y motion. We are 4.3 centimeters in the y direction, and we're not moving in the y direction. How then do we have a speed of 85 meters per second if I said down here that we have a speed of 0 meters per second? Because remember, this is your x motion. This is how fast the wave is moving in the x direction. This is talking about how fast the rope is, oscillating up and down, or the particle, whatever. And they tell us a maximum transverse speed of the particle is 18 meters per second. So I know that at 0, or initially it's not moving, so it's at 0 meters per second, but they tell me that there is a possible maximum speed of 18 meters per second. So that is going to be your v max. And just as a reminder, the speed changes in the y direction according to the simple harmonic motion relations. So what we're actually talking about here is this v max. So maybe we want to indicate that this is also a y. And so that means that this is all y stuff, and this right here is the only information we have in the x. All right, cool. So we have enough to go ahead and tackle part A. Part A, they just ask us for the frequency of the wave, and we'll be giving the frequency in hertz. So that tells us that we want to do the linear frequency. And I know that that frequency is related to omega. Omega is 2 pi f. And just as omega is the sort of centerpiece of simple harmonic motion, it's going to be the centerpiece here as well. And it's going to be the thing that will link your x and y together, because this v is equal to lambda f, and even though our lambda is all an x variable, it is the frequency, or the omega, that actually is going to take us between x and y. So omega, again, cornerstone of solving these problems. And this is like the time when we did two-dimensional motion with just objects moving in a straight line. Like the time was the thing that linked x and y together. It'll now be the frequency, which is kind of just a reworked time. It's an inverse time. All right, so we are asked to find the frequency of the wave. Good, and I know I need to find omega. And the tools that I have to work on here is that I have Vmax of y. I never finished writing it. Mine happens to be 18 meters per second. So I have the Vmax, and I know from my last page that I can just use a simple harmonic motion equation. So Vmax is equal to omega times Ymax, and Vmax is 18. I need omega. Do I know Ymax? Well, I know these two things. I know that this particle at this time and location is displaced by 4.3 centimeters. And I also know that it's not moving. If it's not moving, remember your velocity and your position are 90 degrees apart because one is a sine and one is a cosine. So if you have no velocity, that means that you're at a maximum position. Similar to how when we had just projectile motion, if your y velocity was 0, you're at a max height. If your y velocity is 0 here, then you're at some maximum of that sine function that we defined a few slides ago. So all that is to say that we have 4.3 centimeters for our y max. It's just sort of intuited from the fact that we also know it's not moving. And want to make sure that we're not using centimeters here, so it'll be 0.043. Excuse me. And then we solve for omega. And I don't know what that would give us. It would be something like the 100. No, it's gonna be twice as much as like 190. It's somewhere around 400. Anyway, point is, we can solve for omega pretty quickly, and I'm just going to kind of generalize here. That's going to be like 400 radians per second. I actually will probably need it eventually. So, well, whatever, it's fine. Yours is going to be different anyway. Okay, so this is your omega. This is not the frequency that we're after. We are after the linear translational frequency f, and that's just going to come from omega is equal to 2 pi times f. So 400 equals 2 pi f, and then you can solve for your frequency just by dividing whatever your omega is by 2 pi. All right, I'm gonna have a different one there, but it'll be somewhere around 60. And great. So now that we have our omega, especially, I probably should have actually found mine. But now that I have omega, I know that's going to kind of be the key that'll carry me through. I'm probably going to use that in most of my calculation. In part B, they asked me for the wavelength of the wave. The wavelength, remember, is an x measurement. It really only impacts the x. The wavelength doesn't really show up in the y. It just shows up in that y of xt function with the wave number in the inside. But if I need to find the wavelength, it's going to be from the x. So how am I going to do it? Well, this is your v equals lambda f velocity. So for part B, I'll just do v equals lambda f. And looking at what I'm given here, I know that my v is 85. And then if I want to find lambda, I just use my frequency that I just found in part A. So my frequency, like I said, probably somewhere around 60 hertz, and then just a one-step calculation to find your lambda. So as I mentioned, these problems, there's a lot of parts, but most of them are going to be just a one-step calculation kind of thing. Part C, they're going to ask us for y maximum. Well, we actually just answered that. It's whatever is given right here, because that particle is not moving. So that corresponds to a maximum. Okay, cool. So that's our y max. It's just whatever was given. And then Part D, they're going to ask us for our wave number. How do I find the wave number? Well, I have one equation in terms of the frequency and lambda. Now that I have lambda and the frequency, I know that k is 2 pi over that wavelength lambda. So I just plug in the lambda that I found in part B. One simple calculation. Part E, they asked me to find omega. How do I find omega if I have both lambda and f now? Well, remember, omega is 2 pi f. So I just plug in the frequency that I found in part A and multiply by 2 pi. In part F, they're going to ask us to find the phase shift. And let's see. So our phase shift is going to correspond to, it's kind of, well, this actually maybe requires a little bit more of an explanation. So for part F, we're looking for the phase shift. This is, as I mentioned, you have kind of this one problem where you need to find the phase shift. And what they've told me, if I were just to try and plot one single sine wave, okay, they've told me that for the initial condition, when both x and t are 0, we know that that point happens to be at a maximum. So it's up at the amplitude, right? We got that, we're good. That was how we got the answer to part C. However, if this is a maximum, then that means that this wave is going to come down and then come back up. Notice this is actually a cosine. What they want us to do is they want us to give this equation in terms of sine. So I actually just want one period of the sine wave, which would go back. You'd have to sort of extend it backwards like that. So one sine wave is actually this right here. It has to start and end it has to start at 0, go up to the positive maximum, and then come down and then return to 0 again. All this is to say that sine of kx and omega t, we'll talk about if it's plus or minus in just a second, but sine of kx plus or minus omega t is describes a wave that looks like this. In order to get the actual waveform that has been described to me, given my initial conditions, I need to shift this waveform backwards by exactly 1/4 of a period. So in terms of a phase, we know that one whole phase is 2 pi. If I want to shift this thing backwards by 1/4 of the phase, that means that my phase shift has to be 2 pi divided by 4. That's 1/4 of a phase. And then that'll simplify to pi over 2. And then as far as if it's positive or negative, a shift to the left is positive, a shift to the right is negative. This is why we have the minus plus. Yeah, I'll do the 1/4 one more time. Let me explain that one more time. So just to reiterate, they do tell us that based on these two initial conditions, we know that the point at 0, at x equals 0 or t equals 0, but I guess in this case, we'll talk about it in terms of x. So the point at x equals 0 is at the maximum amplitude, the maximum positive, amplitude, and it's not moving. So that's how we know that that's maximum, and that's your initial condition. So that means that your point, the only point that we have is we know that at 0, 0, we're at our maximum up here. I know because it's going to be a sine wave, I know it's going to go up and down between a positive maximum and a negative maximum as we go to the right and to the left. So I know this is going to come down and then go back up and then go down, it'll keep going that way. And that'll be similar on the other side. It'll look like this. Now what I want is, since I'm writing a sine equation, I want to know where I have one period of a sine wave. It's cosine that goes from the top up here down and then back up. That's one cosine, but the equation that I'm using has sine of kx plus or minus omega t. So in order to get a sine wave out of this that is going to go through this point, one single sine wave is just going to be this piece right here. This is one sine wave. This is one phase of it. This is one wavelength. Those are different words for all of that. I know that this is going to correspond to a total of 2 pi. So that's where the 2 pi comes from. Ultimately, what I'm doing is I'm shifting a sine wave. This is just sine as it naturally, whoops, I need to make sure that this lines up. This is what your sine wave would naturally look like. In order to get the sine wave that has been described to me by my initial conditions, I need to shift that yellow sine wave so that it matches up with the red one. So I need to shift it in this direction, which is a positive phase shift in the negative x direction. And how far do I need to shift it? Well, one way of looking at this is to say how much of my sine wave overhangs or is in the negative. That just happens to be this piece right here that we have shifted to the left side of the y-axis. And this is only 1/4 of the sine wave. So it's 1/4 of the sine wave. So again, the sine wave is 2 pi long. That's not exactly, it's not the wavelength, but that's a phase. So we have a phase of 2 pi. And I know that I just want to shift it by a distance that is equal to 1/4 of that 2 pi. So I'm not sure if that explanation is also as confusing as the last one. I'm trying to think of another one. I'll probably give a more mathematical one. Okay, cool. All right, tight. Then we'll go ahead and leave that at that. The last thing in this problem, I'll just do this sort of off to the side. Part G just asks for if we have a positive or negative omega. Remember that plus or minus. So remember it's minus or plus. A minus corresponds to the positive x direction. A plus corresponds to the negative x direction. And they tell us right on the first line of the problem that our wave is moving in the positive direction. So that means that we need to just choose the negative sign because a negative sign corresponds to a positive direction. Another explanation for, by the way, why that is flipped that way, it's the same thing that happens with the phase shift. It's just a result of the mathematics. A movement to the left is actually a positive phase shift. That's why this is plus pi over 2 and not positive pi over 2 and not negative pi over 2. Okay. Tight. All right. Problem number 8 is going to be similar. I'm not even sure if we introduce, there's like one other equation that we're going to need, and it doesn't even come into play here. All right, so let's go ahead and look at all the information that they give us. They tell us we have a sinusoidal transverse wave. Of course we do, because that's the chapter we're in. And they give us a wavelength. So we'll start with that. Lambda is 16 centimeters. Again, units. We need to, whoops, try that one more time. Cool. We know that we need to use meters to do any of our calculations. And all right, displacement of the string particle at x equals 0 is given in our figure, and our figure just looks like a normal looking sine wave. But they're giving our displacement as a in terms of t, the time. And the scale of the vertical axis is set as well. So why would I need the scale of the vertical axis? Well, that scale is going to represent the maximum and minimum, or the amplitude, in other words. So I can go ahead and use that value. That y sub s is going to be your y max, and that's 2. That's also centimeters. We'll also need to convert that before we use it. And they tell me we want, kx minus omega t plus phi. That sounds good. At t equals 0, is a plot of y versus x in the shape of a positive sine function or a negative sine function. So, let's see, why would it be inverted? x equals 0. Okay, so the plot that is given is for the point at x equals 0. And that point is going to move. It starts at 0, 0. Here's the plot that everyone is given. It looks like this. And you just have a sine wave. Goes like that. Y sub s. This is y sub s, and this is negative y sub s. And this is a picture of the particle at x equals 0. So this is a function in terms of time for the particle at x equals 0. So this is y of, if we want to do y of x comma t, this is the point at x equals 0. So it's always going to be 0 comma t. And if I go back here and look at my general definition, wherever that went, right here, if I plug in an x equals 0, you'll see that I have a minus or plus omega t, and then of course I also have the plus phi inside of there. So to go back here, I know that the general form of this equation, plugging in x equals 0, would be that this is equal to y max times sine of kx, but x is 0, so that term is 0. And we just have minus or plus omega t plus phi. And in this case, which one am I using, positive or negative? Well, they tell me explicitly that's moving in the positive direction of the x-axis. So that means that inside here, I would have a negative, sign. And that negative sign would give me a function that is a negative sine wave, in other words. Since I know that this is a positive sine wave, I know that this needs to describe a positive sine wave. That means that the only way to make this describe this positive sine wave when I have a negative sign in here is to use a phase shift of pi inside of there. It's kind of a long and convoluted answer to a question that is ultimately more of a mathematical question and not one that that you'll encounter a whole lot when you're doing physics problems. But it is something I suppose that you should be able to reason through. And this is one example, I guess, where we're actually utilizing our sine function itself instead of just using the equations like we did in the last problem. Anyway, all this is to say that when you have a phase shift of pi in there, that means that your function for in part A, they ask about instead of plugging in x equals 0 and writing a function of time, they want to know what would the plot look like if we did a plot of y versus x for the time t equals 0. So instead of this graph gives us y versus t, they say, okay, then what can we say about the y versus x graph? Well, I know that my phase shift is pi. That's going to carry over. And just as I did y of 0 comma t here, I can do y of x comma 0. Over here, kx minus omega t, it was my x that was 0, so my kx term was 0. Now I have a time that's equal to 0, so it'll be the omega t that is 0. And I'll have y max times, we usually do sine and then parenthesis. Now my kx term will be varying with x. My omega t term is 0 because I've set time equals to 0. And then I have plus that phase shift, and the phase shift that we found over here is pi. So y max sine of kx plus pi, this is just an old trig identity. If you have a plus pi inside, that is just a sine function specifically. Sine of y equals sine of x plus pi is equal to the y equals negative sine of x. That's not what the identity looks like. But the point is that sine of something plus pi, if it's phase shifted by pi, this is the same as negative y max sine of kx. Cool. Trig. It's a trig problem. And kind of a convoluted one. And anyway, why is it pi and not just 0? Does a 0 give the same value for sine? So I guess maybe I should have done gone a little bit slower here, done another few steps. Y max sine of a negative omega t. This is I also used a trig identity. I just didn't write it down. Sine of negative omega t is the same as negative sine of omega t. This is just a trig identity. In the context of our problem, we also have a phase shift inside the parentheses. So to complicate this picture just a little bit, y max sine of negative omega t plus phi has to be equal to negative y max sine of omega t plus phi. Now, if my phase shift were 0, since I have a negative sign out in front, if my phase shift were 0 and I were to do y versus t, since I have a negative sign out here, a negative sine wave actually looks like this, which is fine. However, looking at the picture that they give us in the problem, notice this is just a regular positive sine wave, right? So how do I take an equation that looks like this and create a graph that is a positive sine wave? Well, the only tool that I have to tweak is that phase shift right there. And by adding that to pi, I'm able to shift this guy over by half of the phase. And then I'll have a graph that looks like this. And so now what I've done is I've adjusted a negative sine function by pi, and thus I've recovered a shape that is just your normal regular positive sine wave. And I know I want that normal regular positive sine wave because of the graph that was given in the problem. Okay. Cool. All right. I think we spent enough time on that part of the problem. I'm hopeful here, and I believe that the rest is going to be relatively straightforward. Part B. Part B, they just ask us to find y max. I think we already wrote down a y max in our given stuff here. Yeah, that was just a given that it's 2 centimeters. So cool. Part C, they ask us to find k, the wave number. Whoops. Okay, so k is 2 pi over lambda. If I can find the wavelength, then I am good. Oh, they already gave me the wavelength right in the first line. So this is just a given right here. That's a one-step calculation. Part D, they asked me to find omega. I know that omega is, I've got a few different definitions. I know it's 2 pi times the frequency. And yeah, so for this part, I actually do need to do a little bit of work for part D to go back to the graph that's given that we use in part A. We're not going to need to do anything like what we did in part A. We just need to do one thing with this graph, but this is an important tool that everyone needs to be able to do. Okay, so this is a y versus t graph. The frequency, remember, f is in hertz, and this is the same thing as waves per second is a hertz. These brackets just mean that we're talking about units. So 1 hertz is 1 wave per second. How do I find out the number of waves per second from this graph? Well, the graph tells me that this is t equals 0, obviously, and this is t equals 10 seconds. So how many waves per second do I have? Well, what I see in this picture is that I have 1 wave that covers 10 seconds. So how many waves per second or hertz do I have? 1/10 or 0.1 hertz. This is a very important thing that you definitely want to make sure that you can do, that you can read one of these graphs. Since this is time, that means that this is going to correspond right here to the frequency. This is actually, this length is 1 over the frequency, f. If this were a graph of y versus x, in that case, this would be 1 wavelength lambda. You need to be able to do both, and I should be able to just give you a y versus t and a y versus x, and you should be able to give me like the velocity or whatever, a whole bunch of stuff, because between those two graphs, you can find both the frequency and the wavelength. Okay, part E asks us for the phase shift, which we already had to find. I need to delete some of these. I like to keep cool. Okay. There's like a limit to the number of whiteboards I can make. I guess I've been writing a lot here. So yeah, okay, they asked us for our phase shift in part E. And I already found the phase shift, it was pi. So that's your phase shift. And then part F, they ask us for the sign in front of omega. In other words, do we use the minus or do we use the plus? Since we're moving in the positive x direction, we know that our sign on omega needs to be negative. That's your minus or plus rule. And in G, they ask us to find the wave speed. The wave speed is that speed in the x direction, which is just your v equals lambda f. And let's see, we found lambda and f. We have found lambda and f. So yeah, we were given lambda and we just got f off the diagram. So that's probably your most straightforward way. You could also do omega over k if you want to check your work. And then in part H, they ask for the transverse velocity. So this is the wave speed. That's the speed that the thing is moving in the x direction. That's constant, it's just lambda f. The transverse velocity, to go back here, your transverse direction is the y direction. So we need to find this velocity right, or that's the position, but we need to find this velocity right here. Okay. So yeah, so at x equals 0, when our time is equal to 4 seconds, in this case, we can, what's going to be our most straightforward way to do it? I suppose we could do a, trying to avoid doing the derivative, but we are going to have to evaluate it either way. So, and it's not necessarily anything. Yeah, okay. All right. So, yeah, for part H, kind of don't really have a choice here. For part H, we want to find the v, I should call it v sub y of x comma t, which is the derivative of that whole long function. Now we're doing a Calc 3 derivative here, and I know that everyone hasn't taken Calc 3, so I don't want to get into like partial derivatives or how that goes. So I am going to kind of break some rules of math here and just say, we know that the velocity is a derivative with respect to time, right? So just treating everything else the same, we can differentiate, where was it? We can differentiate this function here with respect to time and just treat everything else like it's constant. All right, so I know it's very hand wavy, but the equation that we're starting with, I guess I should write down our equation first as it stands right now. Our equation is y of x comma t is equal to, we had y max times the sine of kx minus omega t plus pi. We could also go ahead and use our trig rule with the plus pi inside to make this negative y max sine of kx minus omega t. And then we'll go ahead and differentiate this. Now, again, as I said, I'm going to differentiate with respect to time. I'm going to treat everything else like it's a constant because I just want to differentiate with respect to time. So I'm just doing a d dt. I know it should be curly d's if you're in Calc 3. I don't want to introduce the curly d's. So we're just going to take a derivative with respect to time. So that's all we need to be able to do in this class. And I just need to do a chain rule. So derivative of sine is going to give me cosine. And so I'll have, I know, a cosine of kx minus omega t. And then I also need a chain rule on the inside. With respect to time, the only thing that varies with time is the omega t here. And the derivative of negative omega t with respect to time is just negative omega. So we have a negative omega that comes out front. Out front, we already have a negative y max. So negative y max times negative omega, those negatives will cancel out. And you have y max omega. And then they ask us to evaluate x equals 0 and t equals 4. So I just need to do v of 0 comma 4, which will be our y max we already have, our omega, we already have, cosine of, our k, which we already have, but that's actually times 0 anyway, so that'll go away. Then we have minus the omega that we found earlier in the problem times our time, which is 4 seconds. Everybody might get a different time anyway. Cool, but then you just plug in all the values that we found so far in the problem, and we're just evaluating to find our speed. Again, how do I know that this is the transverse velocity? The transverse is the y direction. Just tie those two together in your brain. Transverse is y. Anything about like wave speed or wave movement, the wave moves in the x, but the oscillations are in the y. All right. Well, we're already at an hour. I hope you see why I split up these two chapters this way. Okay. Problem number 9. Yeah, okay, we're going to finally introduce the actual mass of the string. String. Yeah, so I've been talking about like particles. I mentioned strings a little bit. There are some dimensions that are associated with the string. I closed the slide that had this guy holding onto the string. You don't need to copy this down again, but here's our guy who is sending a wave pulse down a string, and the string is tied to a post, and he's just shaking this thing up or down to send this wave to the right. This string itself has some physics associated with it. So we know, for instance, that it has a certain length. I did mention that he has to keep it at a taut tension. So that's one variable that's important. We use tau here in this chapter for tension. Now, just as a note, all semester we've used capital T for tension whenever we've seen it. Why are we not using capital T here? Because in this chapter we use capital T for period. So now at the very end of the class, we switch to this tau, this little Greek letter for tension. Anyway, just to mention that. The other thing is that the size of the rope in terms of like how thick it is and how dense it is also going to impact the waveform as it travels along the rope. So we introduce this, it's going to be another Greek letter, it's mu, and mu is just the mass per unit length. So that's sort of a density, right? That is a density. It's like a one-dimensional density. Instead of doing mass over volume, it's mass over length. But that's what's going to be important for the actual calculation of the physics. And these two together allow us to write down another definition for the wave speed, v, and it is equal to the square root of the tension over mu. So the square root of the tau over mu, or tension over mass per unit length. Just as a reminder, this is the same thing. We can kind of put it in parentheses here, but this is your lambda f speed. This is the wave speed. This is how fast we're moving in the x direction. So this goes back into our table, I hope I kept that, this table where we have the x and the y, we also have on the x side that this is equal to the square root of tau over mu. And it'll be very clear when we're going to use this definition because they're going to give you something about a tension or they're going to give you some masses and stuff. If you ever see mass or tension or forces in this problem, this is the only equation where we're going to have something associated with that. I believe we'll see the last problem, problem 10, is a little wonky and there's some physics involved there too. But anyway, for our purposes, problem number 9, I see that I have a tension, I see that I have a mass per unit length, and if you see those on the homework and they're talking about waves, you know, on the exam rather, that's how you know to use that equation. All right, so they give me my mass per unit length, they give me my tension. Notice my mass per unit length is grams per centimeter. Please, please, please convert to kilograms per meter. And they tell me that I have a wave with an amplitude. They give me the amplitude, they give me the frequency, they tell me it's moving in the negative x direction. And then they give me the form of the equation, and they just ask me for y max k omega and the sign in front of omega. All right, so this is another sort of just one-step calculations here. Y max is actually just the amplitude. So that's actually given. And that's part A done. Part B, they asked me to calculate K. I know that K is 2 pi over lambda. And they did not give me lambda. So I have to do a little bit of work here. What's the order that I want to do this? I suppose, yeah, so I know my frequency, and I also have the mass per unit length and the tension. So what I want to do here is I want to use this equation and this one. I set them equal to each other, essentially. And ultimately, I just want to find lambda. So I just need to solve the equation that has, setting both sides equal to each other, root tau over mu is equal to lambda f. I want to solve this for lambda. So, you just divide both sides by f. You have lambda is 1 over the frequency times the square root of tau over mu. And we have the frequency, we have tau and mu. So once I calculate this, then I can just plug the whole thing in on the bottom, divide 2 pi by whatever you get there, and that will be your wave number there. All right. And then part C, they ask us for omega. That's actually even less calculation. Part C, omega is just 2 pi f, where they give me my f already. That, again, I know that the frequency that they give me is f because it's in hertz. And part D, they ask me for the correct sign in front of omega. Again, they tell me in the problem that my wave is traveling in the negative x direction. So I know I need to choose the corresponding positive sign in that minus or plus. All right. That problem's a little nicer. Problem number 10 is horrendous. Okay. So I took a look at this problem last night and considered sort of the given solution and also like alternative explanations and approaches, because I don't think the given solution is necessarily helpful or one that people would be able to sort of arrive at on their own. And again, pedagogically, like, how useful is the problem that is just impossible to do, especially when it's about some like niche topic like the kinetic energy rate. But anyway, I digress. So in this problem, we're given two graphs. Both of them are for the rate of change of the kinetic energy, called dk dt. One of them is in terms of position x, the other one is in terms of time. So to start, this is one thing that I do think that everyone should be able to do. I have these two graphs, dk dt, is on the positive, or rather on the the y-axis of both. My first one is in terms of x. My second one is in terms of time. And the shape of the waves are identical. So we go like this. Okay, that's what it looks like. And we know that this is 0.1 and this is 0.2. On the second graph, it's in terms of time. These are x values, right? X equals 0.1, x equals 0.2. The second graph is the time. So it's going to look like this. And this value is time equals 1 millisecond. And this is time equals 2 milliseconds as well. So I'm going to write here just as a note that we're in milliseconds. All right, so here's the one thing that you should be able to do. All right, I mentioned this a few slides ago, a few problems ago, but you need to be able to read the graph and you need to be able to pull off your wavelength and your frequency off of a graph, off of each of these graphs. So the first one is in terms of x. I know that the length of one single cycle should correspond to a wavelength if I'm in the x direction. And the second one corresponds to time, and I've already done this, but one cycle should correspond to 1 over the frequency, f. So yeah, so I should be able to write these down right off the graph. So the first graph gives me my lambda is 0.1, because that's just one cycle of this graph right there. So lambda is 0.1, and that is units of meters. This one will give me my frequency. This will tell me that my frequency, or rather, I guess, 1 over my frequency is equal to 1 millisecond, which is 10 to the negative third. So this means that my frequency proper is 10 to the third, or 1,000 hertz. Okay, so I have both of those. I should be able to do that. And I think that that's the important part of this problem. As far as actually tackling the problem, I have to do a little bit more work. So there's an equation in the textbook. This is the first time I've ever seen this equation, by the way, which tells you like how fundamental and useful this equation is. But there happens to be an equation for dk dt and another one for dk dx. We have one for each. So the two equations are dk dt is 1/2 mu v omega squared y max squared, and then there's a cosine squared and kx minus omega t inside. Now, putting everything else aside, I know that the most valuable thing here is going to be in the amplitude. And yeah, so they tell me that the vertical axis of my graphs is set by this r sub s value, and it's actually given. My r sub s is 11. The units are watts. So that is your amplitude, right? And we know that whatever's out in front of our sine or cosine, or in this case, our cosine squared, is going to be an amplitude as well. So this right here is your r sub s. All that junk is your r sub s. What's the stuff that I know in here? Well, I am given my mu, so that's given in the problem. My v, I know is lambda f, so I've just read those off the graph. I can calculate that v. My omega is going to be 2 pi times f. So now that I have f, I also know that omega. And the last thing that I need is just the oh, and I'm just solving for y max. So in other words, sorry, I got distracted. I do need to correct one thing I did in the last page. But in other words, let's plug in my value, my 11 watts right here for R sub S, and I just set this equal to the stuff that's out in front and plug in these values. Now, one thing that I do need to correct from the last problem, since this is a cosine squared function, what I've highlighted up here is actually only half of the wavelength and half of the frequency, because cosine squared, because of the squared, it flips the negative part up into the top. When you square a negative, it's a positive. So the actual lambda, the proper lambda, is this whole thing. So that actually makes this 0.2 meters. And the proper inverse frequency is actually this whole thing. Inverse frequency is period, right? So proper period is actually the whole length. It's actually 2 milliseconds, which makes this 500 hertz. Little correction there. Cool. But then once you have that, once you read that, then this is just straightforward, just pulling off the amplitude off of this weird equation. But yeah, and that's gonna be it. That's a wrap on the semester. So yeah, that's it for me. I will be posting something in the next week or so. I'll be posting a review. There will not be office hours next Thursday, but the professor did post about the professor's reviews that will be going on next week. So yeah, thanks for sticking around all semester, especially the people who have come every 11:45 to keep me company while I record this and ask questions and stuff, keep me on track. And yeah, it's been a blast. Good luck with your finals. Good luck with physics too. And everybody have a good day.